Hello ladies and gentlemen, we will now continue our foray into generalized linear models. In the first part of this video we've discussed some introductory theory into the concept, and we will start to work with our new example of generalized linear model. At first we will focus on a problem called discrete regression, and discrete regression generally considers fitting integers. We have some Python code here. We have a notebook that of course will be available to you on GitHub, and in this notebook we consider the ideas of discrete regression. Now, of course, as a standard we import some certain packages. We will be using two functions that generally will help us visualize histograms as the test statistics of our problem, because our results that we'll be analyzing will have the results of multiple we will get samples in form of multiple integers for multiple data points, exactly 1,000 data points for each iteration. So our either prior or posterior simulations will result us with a full sample of 1,000 integers. Those integers will have to be analyzed somehow. One of the ideas is to consider a histogram as a statistic for each of the sampling results. Using such histogram will allow us to reduce the dimensionality of our problem. We'll get our statistic will be a vector function that has multiple elements, because we'll have counts for each of the integers. However, we will be able to compare our results with it. And using that such histograms, we'll be using a ribbon plot that you've met earlier, and the ribbon plot will allow us to visualize the uncertainty of histograms. So for this purpose, we'll be creating a special histogram matrix. So we'll provide our function with a result of sampling, and then a maximal integer value, and we'll compute a function that a value of a big matrix of histograms for each of the samples consisting of 1,000 integers will contain an appropriate sized histogram, and a technical function that will allow us to create a histogram plot that will just make it using appropriate points. So we will be working today on artificial data generated especially for this case, just to avoid discussion of certain problems, and also we could consider this problem as a situation when we have very limited knowledge about our data set. We will have three variables. We have 1,000 measurements of each variable, predictor variable, and of the output. As we can see, the values of the output are contained between 0 and 28, so our integers are in that interval, and our data points are constrained either to minus plus 1 with case of x1 and x3, or 0 to 1 in case of x2. And we'll start with our model with standard prior predictive checks. We will be creating a function that will be using our lambda parameters for our data set, and these lambda parameters, which will be x times beta plus alpha. Here we have a vectorized function in order to improve the computation. We will be using a standard function Poisson log. Poisson log is a function with already built-in a link function. So instead of sampling it like here with determining the exponential of alpha plus beta xi and put it into a Poisson distribution, we're using the Poisson log function, so the Poisson with the log link. And we will be using the RNG, which needs to be supplied a vector, and using that vector will provide us with a table of simulated values. So using a predictive check, we'll be able to discuss how we'll develop priors for our distribution. We add one assumptions. Our assumption is that our coefficients, both for alpha and beta, will be identically distributed, so they will be distributed with a normal distribution with zero mean and sigma. It's this sigma parameter is of more interest because it will contain how much uncertainty we are adding to our model. And using that, we will be able to consider how flat our priors will be. So, in order to avoid multiple recombinations, I've added the prior standard deviation as a data to our prior predictive check model in order to do the computation faster. So, we're providing our data set of 1000 points with 3 predictor variables. Predictor variables are taken from the data frame we've seen before, and we are setting sigma as 10. We're doing 1000 samples for our predictor check. Using such a situation, we have one problem. We get an exception warning. I'm not showing you the console here, but I've copied from the console value, and we got a very interesting message that I wanted to discuss with you. And this message says that log rate parameter 1 is 22.55, so like number, but it must be less than 20.7944. And this number, 20.7944, is present in all those exceptions. What does it mean? Well, as I said before, we are working on the logarithmically linked Poisson distribution. So our values of theta must be being raised, or theta, or in this case alpha plus beta x, are being exponentiated, and this is used as a rate in the Poisson distribution. We are using this linked function in order to have a better computational result. So why the value of 20.7944 is relevant? Well, let's look at this number. This is a relatively big number because when we compute the lambda, so the rate, which is an exponential of 20.74, it is a number that is 1 billion with a bit. So like 1 billion is a bit is a big number, but it's still a number. So why it's being here? It is here because if we compute a base 2 logarithm of this value, we get almost 30, up to a certain rounding. And what is 30? 30 is, I need to correct my data code, with 30 and 2 up to 30 is a limit of the capacity of 32-bit integer. So if our value gets over 20.7944, then we get out of limits of integer and stand signals an error. Of course, if we were using 64-bit integers, then we'll have a much more bigger scope of accessing. But again, when we will be modeling numbers that are greater than billions. So that's the situation that we need to be aware about. So certainly sigma equal 10 will be too large. It will be nice in a linear scale, but in a GLM it is certainly too big. And this is a problem that is recurring in GLMs, and that's why in GLMs we want to use prior predictive simulations in order to avoid such situation, to detect situation when our priors for our parameters would get us out of practical ranges. So what we could do, well, we could choose, for example, sigma equal 2. So we would get us kind of an assumption that if predictors would be all equal to 1, because they are bounded from 0 to 1, or minus 1 to 1, in case of x1 and x3, we can still cover a large scope of numbers, but for sigma with 2, there's like very small probability of getting x beta plus alpha greater than 8, and that would correspond to lambda upper bound of 2980, which would give us the upper value of y around 3000, which is certainly exceeding our expectation looking at the data, because our maximum value of data was 28. So it will give us a very, very flat prior, which is at least in such case. So limit will get still far away from in the limit we'll get far away from observed values, but we are still far away from billions that are possible if our exponential if our linear predictors would get too large. So we can now do the predictions once again. We run the simulation again, and we do not get the same errors. So we can look at our parameters. We have 4 parameters of our model: beta 1, beta 2, beta 3, and alpha, which are all, as it can be expected, normally distributed with a standard deviation around of 2. So everything kind of makes sense. From sampling, our maximum lambda is 2.25 or something. So we our worst case of combinations of predictors has not occurred. So we were at most at 2, and computing our outputs, we can now analyze the histograms, and we will have sample the values of prior predictions. We've computed the integer histogram matrix, and we've padded it in order for plotting. The same we did with the actual data. So we've computed the histogram. The histogram has bins computed by our integer histogram matrix, and those bins are actually bins that give each bin is located for each of integers, and they have edges at half between each integer. So it will look nice, and we will not have problems of 2 variables getting into 1 bin. So we can now plot this situation with our ribbon plot that gives us the uncertainty for each of our samples. As we can see, our data is located a bit more into the middle. Our prior is more 0 concentrated, but still allows values here happening, so we don't have to worry about it too much. So let's go to our posterior inference. Posterior inference in this case will just create a stand model that will, as previously, get number of covariates and number of observations. We use our design matrix, and we have our outputs. Again, we're using the vectorized version of the code in order to make it run faster. And if in such situation we have a vector of parameters beta, which will be slopes in our linear model, we have an intercept alpha, we have a vectorized realization of Poisson log in the model, and we'll also be simulating our full observation from our results using the Poisson log RNG. Our dataset now includes y's, but does not include it does not include sigma, because we've already assigned it to 2, and we will be fitting our model by sampling using Hamiltonian Monte Carlo. In this case, we got our simulations, we got a lot of parameters, and we can extract those parameters, and those parameters we will be able to visualize. So our coefficients for beta 1, beta 2, beta 3, and beta 4 are still following normal distributions. However, they are much more concentrated. As you can see, for alpha parameters, we have 2 with a spread of 0.06. For beta 3, we have a focus around 0.6 with standard deviation around 0.1, which can be observed from the figure. You can check it later by yourself. Similar situation of beta 2 and beta 3. We have very concentrated values of beta leading to our model. And let's see how our predictions look like. And our predictions, again, we've computed the integer histogram. We have the histogram of our outputs previously, and we can plot our results. As you can see, this, because we don't have such big scale as previously, we can now visualize everything. These are our histograms. These histograms, as you can see, do not have the vertical lines between bins, but each of the steps is a bin corresponding to output or our simulation. In the case of the yellow ones, these are the simulated bins which have their own ribbon plot. So the bins from our simulation have certain uncertainty among them, which are of course the biggest in the middle, and they are smaller on this side. And the model isn't terrible, but we can see there are certain systematic differences. Remember, when we are doing posterior predictive checks, so we are simulating from the posterior, we do not expect that our data will be exactly in the in the middle of our simulation. No, but we need to have it possible, and individual deviations are not a problem. The problems are systematic changes. And as you can see, the top of the histogram of our distribution is far away from most of quantiles of simulated histograms. We have also certain extensions in the lower values of lower numbers, and we have a drop at the higher numbers. So we have a systematic difference between our Poisson model and our data. But what can we do with the Poisson with this problem? Because our problem shows us that the Poisson model is not that good. Why? Because while it generates integer, so it's okay for this case, but it does not capture the entire data. So if such capturing doesn't happen, so maybe our distribution of our data is not Poisson with the same variance and mean, but it's something else. And the idea of something else is handled by so-called negative binomial distributions. Negative binomial distributions are distributions of which can be interpreted as Poisson distribution with a varying rate, and that varying rate was being marginalized from a distribution. And there are at least 3 parameterization available of negative binomial distribution. We will be focusing on the dispersion parameterization, which is not implemented directly in STAN because concentration parameterization is, but it has a very nice property. This property is that when the dispersion tends to 0, then our distribution tends to Poisson distribution. What is the bonus of this situation? Bonus is that when we assign our probability distribution for something that is similar to Poisson but allows us certain changes, we still leave it a possibility to stay with the Poisson distribution. So our model we can use using the dispersion parameterization. Dispersion parameterization gives us positive parameters as previously, and the dispersion can be seen as when dispersion is equal to 0, our variance is equal to the mean. So starting with small values of dispersion, we'll be still close to the Poisson distribution. If the Poisson distribution is the best what's possible, we won't have that problem. Of course, more details you can find at Michael Betancourt's website. So using the we can implement our model using negative binomial distribution. For that purpose, we need to add the new parameters called inverse phi. So it's an over dispersion parameters as here, and these parameters can be used for in block transform parameters in order to compute actual phi value. So and we will be needing it because we will need to introduce it to our observational model of negative binomial with the concentration parameterization. That's why it's 2 and the logarithm in order to solve the same problem as with binomial or Bernoulli distribution or Poisson distribution in this case. So we'll be it has a link function already implemented. So we can simulate the same method as previously, using all the checks and diagnostics that give us no problems. Then we can start doing histograms. Beta 1, beta 2, beta 3 and alpha are still in the similar ranges of values. However, phi and in consequence psi, which is the inverse of phi, show us how far are we from the Poisson distribution. And we can see that while phi has a small values, psi has small values, which suggests closeness to Poisson distribution, we can see in the phi histogram that we still have a rather big spread, and it is not approaching Poisson distribution from the observation. So we can repeat our results previously with using this new model and seeing how it fares in a histogram comparison. And actually, if it fares either way, very nice way. We've added the negative. We've replaced the Poisson distribution with a negative binomial distribution with a relatively small estimated dispersion. So because the marginal distribution is between 0.078 with a very small standard deviation. So it's a small value, more concentrated value. It shows us that the systematic differences are lost, because now our model is a bit dispersed in comparison to the original Poisson distribution, and because of that it fits our data rather well. So it is contained in something that can be interpreted as a probability, as the very reasonable variability of the data. So, seeing from that, starting from our model, looking at the data, not knowing what to expect, we can tune the prior in order to avoid certain errors, and then we can perform certain simulations in order to estimate our values. Using Monte Carlo computation, we can evaluate distribution of integers with such histogram as I showed you, and looking at the discrete models, we can start consider selecting appropriate model for the task. In this case, replacing classical Poisson model with the negative binomial, which is similar if there was no proof for it being something else than Poisson distribution. The dispersion parameter should tend to 0, and in this case such model would not be justified. So negative binomial distribution with estimated dispersion parameter fits the data very well. And that will be for this part of video, and for the last part we will have logistic regression.